So students, we start with the first paragraph from your syllabus. So from that paragraph, the first part is about the introduction to fluid mechanics. So in this introduction, we first see what is the meaning of word fluid. Now, as you know, in our universe, we have different matters. So those matters we are classified as solids, liquids, and gases. Now, the combination of both liquid as well as gases we call as fluid. Now, this classification is based on different parameters. The first parameter on which this classification is based is number one, molecular spacing. Now, you can say in gases, the distance between the molecule is very, very large as compared to the liquids. And further, in both gases as well as in liquid, the molecular spacing is more than the solids. So you can say in solids, the molecular spacing is very much less as compared to liquid and gas, and in liquid, the molecular spacing is less as compared to the gases. Now, if we talk about the molecular bonds, now you can say the bond is stronger in solids as compared to the liquid and gas. Now, further, the molecular bonding is much stronger in liquid as compared to the gases. So, in simple words, you can say that the bonds in gases are weak. However, the bonds in solids are strong. In liquid, it is in intermediate state. The second classification is based on the volume and shape. Now, you can say that the solids have both volume as well as shape. Liquid has only volume and no shape. Then in gases, we have no volume and no shape. So that is the another classification of matters we have in our universe. Now the third point on which this classification is based, that is on the basis of shear deformation. Now you can say that, say we have a solid. This is a solid body. Now if we apply a tangential force on this body, say this force, the magnitude of this force is up to the elastic limit. Now what happens? This body deforms, changes its shape, something like this. And when we remove this force, the body comes to its original position again. This is what happens in solids. But in case of liquids, as well as in gases, that we call as fluids, say we have this liquid or a fluid, if we apply a tangential force on it, what will happen? This liquid or gas, or we call as a fluid, starts flowing immediately, means starts deforming as soon as we apply the tangential force. Okay, so now you can say that tangential force to solids within the elastic limit, you can see the body regains its original position. Whereas for fluids, you apply the tangential force and the fluid got a new position immediately. So there is no tendency to restore the original position or shape of the fluid. So on the basis of this tangential force application, we classify the solids as well as the fluids. Now there is one more term, we call it as fluidity. The meaning of this term is the tendency of continuous deformation of a fluid. That we call as fluidity. Okay. Now this is how you classify the different matters, how we say the particular matters are in the category of a fluid. Now next term, now we are going to define as the fluid mechanics. Now the fluid mechanics, this term, this is the study of something. So we divide fluid mechanics definition into two lines, or into you can say 2 points. The first point says, so you can say fluid mechanics is the study of, number one is the physical behavior of fluids and fluid systems. Okay, and the laws governing this behavior. So that is the first point. Okay, so according to first point, fluid mechanics is the study of physical behavior of fluids and the laws which governing that behavior. The second point is the study of action of forces on fluid and of the resulting flow pattern. Okay, so the combination of these two lines is comes under the definition of fluid mechanics. So, in simple words, now you can say that fluid mechanics is the study of physical behavior of fluids and the laws governing that behavior. Then the study of different action of forces on fluids, or you can say how fluid behaves when different forces are acting on that particular fluid or a fluid pattern. So this in this manner you can define the fluid mechanics. Now this fluid mechanics has three branches. First we call as statics, second one is kinematics, and third one is dynamics. So statics means the study of fluid which is at rest. This is the study of fluid which is at rest, that we call as statics. Kinematics means the study of fluid which is in translation, rotation, or deformation. Or you can say the study of fluid which is under motion, that we call as kinematics. Okay. Now under this motion, you can say there is no application of external forces. So then only we can call it as the study of kinematics. The other part of fluid mechanics is the kinematics. If this motion is due to the application of external forces, so that study of fluid mechanics we call as dynamics. That we call as dynamics. Okay. So under this dynamics, we study the acceleration, we study the velocity with the effect of this external force. Okay. So that is the dynamics. Now, if this complete study of fluid mechanics is for water, so that term we call as hydraulics. If water is the fluid only, we call this fluid mechanics term as hydraulics. Now, this hydraulics has three parts. One we call as hydrostatic, hydrodynamic, and hydrodynamics. Okay, this is the study of water only. Okay. Then we have one more term that we call as continuum. Now, the continuum is, we can call it as the continuous and homogeneous fluid medium. Okay, so the continuum we can call as a continuous and homogeneous fluid medium. Now, the meaning of this continuous and homogeneous term is that the part of fluid which is under consideration that is free from all voids or cavities, that may be microscopic or macroscopic. So those voids or cavities within the fluid that we will ignore. That we will ignore. That is the meaning of term continuous and homogeneous. Okay. So if I repeat this term continuum, so you can say continuum is a fluid system which is continuous and homogeneous. Now the meaning of term continuous and homogeneous means that fluid medium is free from any void or cavity. Okay, so that is the meaning of term continuum. Then next we talk about the different types of fluids we have. Now we classify the fluids we have into two parts. One we call as ideal fluid, and second one are the real fluids. So in our universe, there is no ideal fluid is available, but to study the theoretical part of fluid mechanics or fluid machines, we have to consider the concept of ideal fluid. Now the meaning of ideal fluid is fluid which do not deform when, sorry, you can define the ideal fluid as the fluid which is incompressible and non-viscous. Means ideal fluid is that one which have no viscosity and which is incompressible. So that we call as ideal fluid. Now in real fluid, we have different categories. First category we call as Newtonian fluids. The second category is of non-Newtonian fluids, and third category is of ideal plastics. Okay. Now real fluids you can call, these are the fluids which have some compressibility and viscosity. So in all these three types, we have some compressibility as well as some viscosity. So now we take these fluids one by one. Now the Newtonian fluid we call as the fluids which obeys Newton's law of viscosity. Now this law is tau is equal to mu du by dy. Now here the tau is shear stress, mu is viscosity of fluid, the term du is change in velocity, and term dy is the distance between two successive layers. Now we discuss this law in detail when we discuss the various properties of fluids. So here you just know this is our Newton law of viscosity. So fluids which obeys this law we call as Newtonian fluids. The example for Newtonian fluids we have air, the another one is water, then another one is kerosene. Okay. Now the fluids which do not obey Newton's law of viscosity, that we call as non-Newtonian fluids. So here tau is not equal to mu du by dy. But there is some relation between tau, mu, du and dy. So that relation we can write as tau equal to k times du by dy raised to power n. So here k we call as consistency index and n we call as flow behavior index. Okay. So n is the flow behavior index and k is consistency index. So depending upon the value of n, we have now two different types of non-Newtonian fluids. The first type of non-Newtonian fluids that we call as sorry that we call as uh, pseudoplastics. The second category we call as dilatant. So pseudoplastics and the dilatants. These are the two categories of non-Newtonian fluids. The difference is for pseudoplastics n is less than 1 and for dilatants n is greater than 1. So you can say for pseudoplastics, fluids which has flow behavior index n less than unity are called pseudoplastics. The example for pseudoplastics fluids are milk and then blood. Okay. And for dilatant, you can say the fluids which has flow behavior index n greater than unity. And the examples for this type of fluid we have printing ink. The another example is concentrated sugar solution. Concentrated sugar solution. The another example. The another example of dilatant fluid is aqueous suspension of rice starch. Okay, so printing ink, concentrated sugar solution, and aqueous suspension of rice starch. These are some examples of dilatant fluid. Now the third type of fluid, for real one, we have the ideal plastics. So the ideal plastics are those fluids which do not deform when stressed up to certain limit. So do not deform when stressed up to certain limit. Okay, and beyond that, they behave like a Newtonian fluids. So such type of fluids we call as ideal plastics. The examples for such fluids we have the sewerage sludge, the one example. The another one is water suspension of clay and fly ash. So sewerage sludge, the one example. The another one is water suspension of clay and fly ash. So that are the examples of ideal plastics. So these are the different types of fluids we have. Now, if we try to draw a graph or a plot, the plot is between tau along y-axis, that is the shear stress, and du by dy, du divided by dy, that is along x-axis. So for Newtonian fluids, tau is directly proportional to du by dy. So there is a straight relationship for Newtonian fluids. So for ideal fluids, there is no viscosity. So you can say along x-axis, we have the ideal fluids. For ideal plastics, you can say there is no deformation up to certain point, and beyond that, the fluids behave like a Newtonian one. So this is ideal plastic. Okay. Now for pseudoplastics, n is less than one, so curve is something like this. And for dilatants, the curve is like this. So this is dilatant. So this is how you can represent different types of fluids along tau and du by dy curve. So these are the different types of fluids we have. So next we discuss the different types of fluid properties. So that we discuss in next part of lecture. Okay, thank you.